Right, here what we're doing is we're looking at the Cartesian equations for parametric equations which have sec and tan in them. So what's sec and tan are? Sec is 1 over cos and tan is sine over cos. And when you have this kind of parametric equation set up, you need to use a different identity. Now, we were using this lovely Pythagorean identity, sine squared t plus cos squared t equals 1. Unfortunately, that doesn't have sec or tan. But the cool thing is that we can actually divide both sides of this equation by cos squared t, and you'll see what happens. I'm going to divide this side by cos squared t, and you can see here, looking at the left side, this is sine over cos. Sine over cos is equal to tan, and because it's got the squared on each side, it's tan squared. Cos squared on cos squared, well, that's 1. 1 on cos, well, that's sec, and because it has the squared, it's sec squared. So this equation here is the other version of this one, and it's the one that involves sec and tan, which is really useful because there's one situation where this one is going to be the better one to use than the sine and cos, and that's in this situation. I'll just do it in a different colour. If I take or keep the one on this side, I'm going to take the tan squared to the other side. What we have is sec squared t take tan squared t equals 1. This version, in the big blue box, is very similar to this now. So you've got the one on the right hand side, you've got two squared terms, but the big deal is that in one of them the squared terms are added, in the other one they're subtracted. And this is the difference between having a circle or an ellipse, which you'll have here, and having a hyperbola, which you'll have here. Alright, so we're going to use this one because you've got sec and tan. So here, first thing we're going to do is write down our equations. Now, very similar to previously, solve this for the sec and solve it for the tan. This is x on 3, and y is 4 tan t. Solve this for the tan. Tan t equals y on 4. So now what we can do is we can put both of these into this equation, and we're going to end up with sec squared, which is x on 3, all squared, minus tan t, which is y on 4, all squared, which equals 1. And I'm just going to expand that so it looks a bit nicer. X squared on 9 minus y squared on 16 equals 1. And that is our Cartesian equation. So we very quickly got the Cartesian equation from the parametric. Now what we need to do is two other things. We need to describe the curve. We're going to do that just by doing a quick sketch. Okay, now I know from this particular setup, this is a east-west hyperbola because you've got the x first, so that means you're going to have a graph that looks like this. Boom, boom. And it's because the x is first, most of the action is in the horizontal axis. So we can first of all find our asymptotes for our graph, which is really important. So we're going to, I'll just put the working down here. To find asymptotes for hyperbola, all you have to do is instead of making or letting these two things, the two squareds, difference of these squared terms equal 1, let them equal 0. What that's going to do is then get these things to cancel out, and that's impossible on the graph of the hyperbola. So I'm going to then solve. I'm just squashing it all together so we've got a bit more room. 16x squared on 9. Take the square root of each side, gives you y equals plus or minus the square root of 16 is 4, square root of x squared is x, square root of 9 is 3. So your asymptotes are here, plus or minus negative plus or minus 4x on 3. Now, for the graph, we actually have a really important restriction here, which is on the t up here. So what we should do is actually look at x equals 3 sec t and consider what happens, and y equals 4 tan t. Consider what happens for different values of t. So with these ones, when t equals pi on 2, you're going to end up with x equals 3 over cos of pi on 2. Now we know cos of pi on 2 is actually going to be 0. This is 3 on 0, which is infinity. It's infinitely big. And y equals 4 tan pi on 2. And tan of pi on 2 again is infinitely big. So this is not very helpful to us. And you'll actually get the same thing happen with this 3 pi on 2. So the problem there is, well, what do we do? That's not helpful. I don't know which branch I'm going to be interested in for the hyperbola. It's just going to be going off to infinity. Well, think about the t values that they're giving you. I'm just going to draw a picture for you. We're looking at these t values between pi on 2, which is here, all the way through to 3 pi on 2, which is also negative pi on 2. We're only interested in these values of t here. That's the t we're interested in. So these values here give us infinity. It's a bit silly. So usually the best option here is to pick a t value that's in between and see what that gives you. So let's try what happens when t equals pi. That's in between, going around the circle. So we'd have x equals 3 over cos of pi. We know cos of pi is negative 1, so that would be x equals 3. And we then know that if we substitute y equals 4 tan of pi is 0. So that means we know we have a point, which is this point, ooh, pen's gone funny, which is negative 3, 0. And that particular point, I'll just put that with better brackets, that point there is going to tell us which branch of the hyperbola we're interested in. So now we can sketch all of this together. We've got our Cartesian form here in the box. I'm just going to put it together nice and quick. We've got our hyperbolae and our asymptotes. The asymptotes go through the origin because they're just quite boring linears for x on 3 and y equals negative 4x on 3. And then we've got hyperbola. Now we're only interested in the side that includes negative 3, 0. That is right here. So that must be that branch there. So this restriction here has actually kept us to 1/2. And it's interesting because you can see this is the left half of t. It just happens to be the left half here of the hyperbola as well. So be very careful when you're dealing with these particular situations. Always look at your domain restriction. That can actually restrict you to only looking at part of the Cartesian equation as a graph.